Hey everyone, welcome back to trigonometry. This is going to be lecture 2 of the course, and in this section we're going to get into the trigonometry part of trigonometry. So we're going to start with right triangle trigonometry, and the main goals of this section will be to define the trig functions and in terms of right triangles, and to develop a handful of, introduce / develop a handful of sort of fundamental trigonometric identities. Okay, and so we're going to go ahead and start with the right triangle trigonometry piece by introducing what we mean by a right triangle. So many of you will have heard of this, some will not. So I'm going to operate with the assumption that you haven't heard of what a right triangle is, and I'm going to define it. A triangle that includes a 90-degree angle, a right angle, is called a right triangle. Okay, so a triangle that includes a 90-degree angle is what we mean by a right triangle. A 90-degree angle is referred to as a right angle. Okay, and so here's your representative triangle here, and a right angle is denoted by a kind of a box at the location of the angle. Okay, and so this would be an example of how we might represent a right triangle. Now, when it comes to right triangles, there's a handful of different terms that we use. So we're going to go through some of that terminology quickly here. So the two sides of the triangle, of the right triangle, that are adjacent to the right angle, right, namely this side and this side. Notice this other side is opposite the right angle. So these two sides we refer to as legs. We'll call this leg 1, and this we'll call leg 2, right? They're the legs of the right triangle. And then the side that's opposite the right angle we refer to as the hypotenuse. The hypotenuse. It's the hypotenuse of the right triangle. Okay. And so frequently when we're doing trigonometry with right triangles, they'll be in reference to either this angle, theta, what's called theta 1, or this other angle, theta 2. Right? The right triangle trigonometry will be done in reference to these two angles. The right angle is not what we'll usually be doing the trigonometry with. Okay, so this is a right triangle. Some terminology is the legs of the triangle and the hypotenuse of the triangle. Okay, now I'm sure many of you have seen right triangles before, certainly. One of the most famous theorems in all of mathematics is about right triangles, actually, and it's called the Pythagorean Theorem. The Pythagorean Theorem. And so Pythagoras was a Greek mathematician, and this theorem is named in his honor. And so what the Pythagorean theorem says is that given a right triangle, all right, I'll just draw the right triangle, right, where you've got one of the legs denoted as A, the other leg denoted as B, and the hypotenuse C. Given a right triangle of this sort, the following relationship holds. All right, and the relationship is the famous a squared plus b squared equals c squared. Okay. And so what this is basically saying is that the length of this leg A, when you square that length, and the length of leg B, when you square that length, when you add those two squared lengths together, a squared plus b squared, you get the length of the third side of the triangle, the hypotenuse, and that's equal to c squared. Okay. And this holds for all right triangles, no matter how small or how large they are, how steep this angle may or may not be. If it's a right triangle, then the Pythagorean theorem says that the legs have this relationship to one another. Okay. Pythagorean theorem is a very famous theorem, not simply because it's very, very simple yet kind of beautiful. It tells you a lot about, it just points to a really amazing structure with regard to the nature of these triangles. But it's also insanely useful. It's everywhere in mathematics, from the simplest domains to the most complex domains. Pythagorean theorem shows up all over the place, repeatedly, over and over again. Okay, for our purposes, we'll use the Pythagorean theorem in a handful of trig identities, but the sort of fundamental value that we'll derive from it, well, there's lots. I shouldn't even say it. One of the main use cases for the Pythagorean theorem for us will be determining the value of the sides of a triangle if one of them is unknown. Okay, so let's see an example of that. Okay, so let's see an example of that. So let's solve for the missing side. Okay, and let's say I've got my triangle here. Okay, and let's say I know that A is equal to 5, C is equal to 12, but B is unknown. Now notice here I've swapped the sides, the legs. These are just names I'm giving to the legs. It doesn't really matter. The relationship holds the same no matter which one I call A and which one I call B. So don't be confused by that. Okay, so we're given a triangle. We're told, well, we know it's a right triangle, and we know what the length of side A is, and we know what the length of side C is, but we do not know the length of side B. Our task is to figure out what the length of side B is. Okay, and so this is a right triangle. We know 2 of the 3 sides, so we're going to make use of this equation here to find the side B. Okay, so we know that a squared plus b squared equals c squared, right? That's the Pythagorean theorem. That's the Pythagorean theorem. What I need to do is I need to figure out what b is. So I'm going to do some algebra to the expression, right? And I'm going to subtract a squared from both sides, basically. And I have b squared equals c squared minus a squared. Okay. Now, I'm not interested in what the square of the side b is, right? B squared. I need to know what b is. And so I'm going to take the square root of both sides. Okay, and that'll tell me that b is equal to the square root of c squared minus a squared. Okay, so whatever this happens to be, that's what the length of b must be, just by using basic algebra, right? Just doing algebra to this equation. So let's plug in the values, right? So b is equal to, now c we're told is 12, so that's 12 squared, minus a is 5, so 5 squared. Okay, and we know that that's 12 squared is 144, 5 squared is 25. Okay, and so that's equal to the square root of 119. Okay, and you can plug that into a calculator, and you'll see that it's just short of 11. So it'll be like 10.9 something, but 10.9. Okay, so the side B, this guy here, we now know that is equal to 10.9. Okay, now if you're given 2 sides of a right triangle, you can always use the Pythagorean theorem to find the third side. Okay, you can always find the third side. Okay, all right, so that's just an example of how of the Pythagorean theorem and how it can be useful to us. Okay, and you'll see more examples if you get into homeworks and start looking at more example problems. Okay, we're going to shift gears ever so slightly. We're still talking right triangles, but we're going to kind of build up now to the trig functions themselves. What are they? Okay, so let's say we're given a right triangle. Given a right triangle, and I'm going to just write it out here. Okay, so I've got my right angle, and I'm going to say this is side A, that's side leg A, leg B, and the hypotenuse is C. Okay, and then I'm going to denote this angle here as theta. That's the angle of interest. Now, theta in a right triangle, theta is guaranteed to be an acute angle, right? So notice theta is guaranteed to be an acute angle in a right triangle. Why is that? Okay. Well, why? The reason is because we know that triangles, the sum of all three angles has to equal 180 degrees. So the sum of all three angles of a triangle must equal 180 degrees. Now, that may or may not be something that you're familiar with, but that is the case. Now, if one of the three angles is 90 degrees, that means the other two angles, namely the angle I've marked theta and this other unmarked angle up here, those two angles together must sum to 90 degrees. So the remaining two angles must sum to 90 degrees, which implies that they're each less than or equal. Well, less than 90 degrees, right? Because there's two of them. If this is 90 degrees and that's 90 degrees, then this is 0 degrees, and you don't have a triangle. So the implication here is that they're both less than 90 degrees. Right, and that's the definition of acute angle. Okay, all right. Right, so when we're dealing with right triangles and we're dealing with right triangle trigonometry, we're dealing with acute angles only. Okay, and that may or may not be important in a moment. Okay, all right. So now what we want to do is we want to talk about, so given our triangle, okay, so we've got our theta, we've got our 90 degrees, and we've got A, B, and C. The right triangle trigonometry is based on ratios of the sides of a right triangle. Right triangle trigonometry is, well, I'll say, built on the ratios that exist between sides of a right triangle. For example, one ratio is A over B, right? So namely in this case, the longer leg divided by the shorter leg. That's one ratio. Another ratio would be B over A. Okay, that's the short leg over the long leg. A third ratio would be A over C. Right? In that case, it would be this long leg divided by the hypotenuse. And the reciprocal would be C over A, the hypotenuse over the long leg. And then you've got B over C, right? The short leg over the hypotenuse, and you've got C over B. Okay. Are there any other ratios that are possible? And by ratios, I mean dividing one side by another. No. These are all 6 possible ratios. Okay, these are all 6 possible. There are exactly 6 ratios that we can form from the sides of a right triangle. Okay. Right, now notice it doesn't matter, well, I won't go there. These 6 ratios are how we define the trig functions, the trigonometric functions, when we define them in terms of right triangle trigonometry. So these 6 ratios are how we define right triangle trigonometry. Actually, I'll say these 6 ratios are how we define right triangle trigonometric functions. Okay, and we'll come back to, the reality is that these trigonometric functions that I'm about to lay out can be defined in a variety of ways. Right? This is one way, and this is possibly the most simplistic way to think about it. Depends on who you ask. It's certainly one of the most simplistic ways to think about it. It's a good way to start. That's what I always say. So here they are. I'll write them out. Let me, yeah. So the first one is the sine of theta. Okay, the sine. And now if you were to spell this out, I'll do that too. The sine of theta is how you would say this. Okay, and the sine of theta is equal to b over c. Okay, it's equal to basically this ratio here. That's the sine. Okay, then you've got the cosine of theta. The cosine of theta is equal to a over c. Okay, so that's this one. Then you've got the tangent of theta. The tangent. And the tangent is b over a. Okay, so that's this one. Okay, so you've got b over c, a over c, and b over a. Okay, now notice these two here were reciprocals of one another. Those two were reciprocals of one another. And these two over here were reciprocals of one another. Right, so b over c is the sine. And so c over b is something called the cosecant. It's the cosecant. And it has this relationship with the sine where it's basically the reciprocal. Whatever the sine is, the cosecant is 1 over the sine. Or you can flip the ratio upside down if you like. So that's the c over b. And then the a over c was cosine, and so c over a is something called the secant of theta. Okay, and it obviously, you can see, has this reciprocal relationship with the cosine. Cosine is a over c, secant is c over a. Okay, and then the tangent is b over a, and so what we call the cotangent is a over b. Okay, and so that these guys here, sine, cosine, tangent, cosecant, secant, and cotangent, these are the 6 trigonometric functions. These are the 6 trigonometric functions. Okay. Okay. So sine, cosine, tangent, cosecant, secant, and cotangent are the 6 trigonometric functions. Right, and most of what we study in trigonometry revolves around these guys. All right, so you may be saying to yourself, how will I ever remember these definitions? How will I ever remember this? Well, so first of all, for my class, you can have a reference sheet if you like. There is a very nice way to remember these, though, that people have used over the years, and it is this word, so ka toa. So when I was in high school learning trigonometry, this is how we thought of it, SOHCAHTOA. And it's an easy enough word to remember, SOHCAHTOA. And the reason it's valuable is because it's a mnemonic device. So here the S means sine, the O means opposite, and the hypotenuse, and the H means hypotenuse. Okay, and so what does that mean in terms of our trig functions? Right, so A, B, C. Right, that's how we had it written out. Now, notice that if this is my theta of interest, then B, the B leg, as I've written it out here, is the opposite side. It's the leg that's opposite theta. Okay. The A side here is what we call the adjacent side. It's the side that is adjacent to theta, meaning it's touching theta, right? It's next to it. And then C up here, of course, is the hypotenuse. This is a right triangle. It's going to have a hypotenuse. Okay. And so SOHCAHTOA tells me that the sine function is the opposite over the hypotenuse. So remember, the sine of theta was opposite over hypotenuse. It was B over C, wasn't it? If you look at your notes. Right, so you can remember it that way. What about the ka? So that's the sine is opposite over hypotenuse, B over C. The ka would be cosine adjacent hypotenuse. Right, so the cosine of theta is equal to A over C. You could also just remember it as adjacent over hypotenuse, A over C, the side that's touching theta divided by the hypotenuse. Okay, so that's the ka in SOHCAHTOA. And then, of course, the toa is the tangent, and it is the opposite over the adjacent. And so we saw that the tangent was B over A, which is, you can remember it as opposite over adjacent. So sine, cosine, theta, or sine, cosine, tangent are all can be remembered in terms of this mnemonic device SOHCAHTOA. Now, what about the other three? Well, the other three, you just have to remember which one each of them is the reciprocal of, right? So tangent, well, the cotangent is easy. Cotangent is the reciprocal of tangent. Right, so cotangent is the reciprocal of tangent, so cotangent of theta is A over B, which is adjacent over opposite. Right, so you can just remember that based on, tangent, cotangent, they go together. Now the cosecant and the secant is where things get a little goofy, because it turns out the secant is the reciprocal of the cosine. So the secant of theta is whatever cosine is, but upside down. So it's C over A. It's hypotenuse over adjacent. All right. C over A. And then the cosecant is the reciprocal of the sine. So cosecant of theta is equal to whatever the sine is upside down, so c over b. And that's hypotenuse over opposite. Okay. So however you want to remember this, certainly SOHCAHTOA is tried and tested for sine, cosine, and tangent, but where it might come up short is with the reciprocal identities, and so you'll just have to figure out how you want to remember that. I mean, to me, it's just you want to intuitively think that the cosecant is the reciprocal of cosine because they both start with co. You just have to remember that that's not the case. That secant goes with cosine and cosecant goes with sine. So to me, that's easy enough to remember, but again, you can also just write it down and you can, reference it in your notes. You'll never be asked to derive anything from memory, at least not in this class. So, okay, very good, very good. Let's do an example here. Let's do a quick example. So let's say, here's the example. Given the triangle, I'm going to write it out in a second. Our task is going to be to find the value of the 6 trig functions. Okay, and so my triangle is a right triangle. Okay, not drawn to scale or anything, but I know that this is 5, this is 3, and the B leg is unknown. The opposite leg is unknown. Okay, so so our goal is to find the 6 trig functions. So if we know all 3 sides, then the trig functions are just, you just pull them off. They're ratios of the sides, right? And you just have to remember which ones. But we don't have all 3 sides. We're missing B. So let's go find B first. So step 1 here would be to find B. And we're going to do that using the Pythagorean theorem. Okay. And so we know that a squared plus b squared equals c squared. We need b. We have a and c. And so b squared equals c squared minus a squared. And so b is equal to the square root of c squared minus a squared. Okay. Plugging in our numbers, we see that b must be equal to, c is 5 and a is 3. So 5 squared minus 3 squared. Okay, and so that's just 25 minus 9, right? And that's the square root of 16, which is a nice round number of 4. Okay, so that's easy enough. We now know the side opposite theta, we know the side adjacent theta, and we know the hypotenuse 5. So we have all 3 sides now. We can just crank out all of the trig functions. So let's start with the sine of theta. Let's try to use SOHCAHTOA here. So sine of theta is equal to so that's the O over H, right? And if this is theta, then opposite is this guy, 4, and the hypotenuse is 5, so 4 over 5. Okay, so that's the first one. The cosine of theta is going to be, that's the ka in SOHCAHTOA, so that's CAH, so cosine is adjacent over hypotenuse. And if this is theta, this side adjacent to it, the leg adjacent to it is 3, and 5 is the hypotenuse, so that's 3/5. And the tangent of theta is TOA, so that's opposite over adjacent. And so opposite is 4, adjacent is 3. Okay, so there's sine, cosine, and tangent. 4/5, 3/5, and 4/3. Now to get the other 3, we just have to remember that cosecant is the reciprocal of sine. So cosecant of theta must be hypotenuse over opposite, and so it must be 5/4. The secant is the reciprocal of cosine, and that's h over a, and so that's 5/3. And then the cotangent is the reciprocal of tangent. So cotangent is adjacent over opposite, and that's 3/4. Okay, so here we are. We've got the 6 values that we were asked to find. Okay, and so that is an example of finding the trig functions, finding the value of the trig functions given a right triangle. Okay, and this one had the added challenge of identifying a missing side before we could find the trig functions. All right, very good, very good. Okay, so I think we'll switch gears now and talk about using, so we'll talk about fundamental identities. So fundamental identities. Okay, and we'll use this term identities over and over in this class. You can kind of think of an identity as an equation or formula involving trig functions. And these are, we would never, if we started trying to enumerate all of the trigonometric identities, we would never run out of possibilities. There are infinitely many of them. What we'll do in this class is we'll go over a lot of them. We'll go over the key ones, the ones that are of most value, both inside of trigonometry and in other areas of mathematics, where, you know, things that, trig identities that come up in calculus and elsewhere, like things, the identities that are the most useful and valuable. Okay, and probably the one that you know is the most useful and valuable to know is the one that we've already really kind of talked about, and that is the reciprocal identities. We've already really talked about this, you know, when we were defining the trig functions. We said that sine and cosecant had this relationship, and cosine and secant had this relationship, and tangent and cotangent did. And so here formally is that relationship. So the sine of theta is equal to 1 over the cosecant of theta. Okay, so that's what we mean when we say that whatever sine is, you can flip it over and get cosecant. So naturally, this works both ways. So sine of theta is equal to 1 over cosecant of theta, and the cosecant of theta is equal to 1 over the sine of theta. All right. And the other ones are cosine of theta is 1 over secant of theta, and secant of theta is 1 over cosine of theta. Okay, so we've seen these. And then the last one is the tangent and the cotangent. So tangent is 1 over cotangent, and cotangent is 1 over tangent. Right, so these are the reciprocal identities. Okay, these are easy enough to remember. These, I think, you could probably commit to memory pretty easily. Okay. All right, and so these are the ones we already talked about, so let's move on to something that we haven't seen yet. And this one is also extremely important. This one is what's called the quotient identities. So quotient should make you think of division or ratios or something. And the quotient identity says that tangent of theta is equal to sine of theta over cosine of theta. And it says, well, and the cotangent of theta, being the reciprocal of tangent, would be the same relationship but upside down, so cosine over sine. Okay, so these are the quotient identities. All right, and this is one where maybe we could figure out why this is true. So why is this true? Why would this one be true? Well, let's remember what the sine, cosine, and tangent are. So sine of theta was b over c, or you could think of it as opposite over hypotenuse. Cosine of theta was a over c, or adjacent over hypotenuse, and the tangent of theta was opposite over adjacent, so b over a, or opposite over adjacent. So this is by the definition of the trig functions, right? And so it's pretty easy to see that if I take the sine of theta and I divide it by the cosine of theta, then I'm doing b over c divided by a over c, right? And that is, so it's important to remember what to do when you're dividing fractions, dividing a fraction by another fraction. The way we, if you don't recall, the way to deal with that is to invert the denominator and turn the problem into a multiplication. So this is equal to b over c, the numerator, times not a over c, but c over a. And so you can see that that's just b over a, right? And what is b over a? Well, that's this guy. That's the tangent. All right. And so obviously you'll get the same answer if you do it with opposite over hypotenuse and adjacent over hypotenuse. So sine of theta over cos theta is opposite over hypotenuse over adjacent over hypotenuse. So that's opposite over hypotenuse times hypotenuse over adjacent, and so it's opposite over adjacent, which is the tangent. Okay, opposite over adjacent, that's this one. Right? So the this identity just follows just basically from the definition. Super easy to derive. Okay. All right, very good. Let's do an example where we make use of some of these. Let's do an example. Okay, so example. So given that the sine of theta is equal to the square root of 5 over 5, and cosine of theta is equal to 2 times the square root of 5 over 5, can we find the value of the 4 remaining functions? Can we find the value of the 4 remaining trig functions? Okay. So yeah, we definitely can, right? So we know sine and cosine. So we can use the quotient identity to find the tangent. Okay, so the tangent of theta we know is sine over cosine. That's what we just talked about. We know the value of these two. They're square root of 5 over 5 and 2 square root of 5 over 5. So we can just put that in here. Right? And we know how to deal with these fractions. Square root of 5 over 5 times this guy flipped upside down. Right? And so we get a lot of cancellation. The 5's cancel, the square root of 5's cancel, and this is just 1/2. Okay, so that's that one. What about, so we know sine, cosine, and tangent. What about the reciprocal functions? Well, we can quickly get the cotangent, can't we? That's just the 1 over tangent. Okay, and so that's 1 over 1/2. And so you can, if you're thinking of it like this as something divided by a fraction, you could say this is like 1 over 1 divided by 1 over 2, right? The 1 on top here is just 1 over 1 if you want to convert that to a fraction. And so you could write this as 1 over 1 times 2 over 1, which is just 2. The other way to think about it, probably the more economic, time-wise efficient way to approach this would be to say, whatever tangent is, if it's a fraction, just flip it upside down to get the cotangent. And so 1/2 upside down is just 2. Just flip it over. 2 over 1. It's just 2. Okay. What about the secant? Well, we know that the secant is 1 over cosine. That's the reciprocal identity. Secant is the reciprocal of cosine. Okay, and so we know that cosine is 2 square root of 5 over 5. Okay, and so that means the secant must be 5 over 2 square root of 5. Okay, and I'm going to take a leap here, and I'm going to tell you that this is actually a better way to write this is to write this as the square root of 5 over 2, and we're going to come back to this in 1 minute right here. Okay, so the secant is square root of 5 over 2. It's really just whatever cosine is, flip it upside down. And then I did some funny algebra here, which I'll show you in 2 seconds. Okay, what about the cosecant? That's 1 over sine. Okay, so that's 1 over the square root of 5 over 5. So that's equal to the 5 over the square root of 5. And again, I'm going to do some funny algebra, and I'm going to tell you what this is in a second, but it turns out that 5 over the square root of 5 is equal to just square root of 5. Okay, and we'll come back to this in a second. All right, and so that is how we would solve this problem. Here we used the quotient identity. Here we could have used the quotient identity, but it's maybe simpler to just flip the tangent result upside down, so we use the reciprocal identity. And for these two, we use the reciprocal identities as well, right? Just whatever cosine was, we flipped it upside down. All right, so here you can see that the cosine was 2 square root of 5 over 5, and so our secant was 5 over 2 square root of 5, so it's just upside down. And the same thing here. Square root of 5 over 5 became 5 over square root of 5, so the reciprocal. Okay, so what's going on with these guys here? What are we doing there? What we're doing here is we're doing something called rationalizing the denominator. So in math, when we're dealing with fractions, there are a lot of conventions. One of the conventions is, if we have a fraction, we like to reduce the fraction. Rather than write 10 over 5, or rather than write 5 over 10, we would write 1 over 2, right? So whenever possible, we take a fraction, we simplify, we make it as simple as possible. And one of the things that you possibly haven't seen up until now is the case when you have fractions that have radicals in their expression, right? So for example, here I have the square root of 5 written in my fraction. Now there's nothing wrong with having the square root of 5 as part of your fraction, but mathematicians typically would like to have radicals like that in the numerator. Right? If you remember, a lot of arithmetic takes place in the numerator. All your addition and subtraction is all about the numerator, right? Getting common denominators, but once you have those common denominators, all of the action takes place in the numerator. And so as a matter of form, we tend to prefer to have radicals expressed as numerator values only. And so when we have 5 divided by 2 square root of 5 like this, it's not wrong. It's not that it's incorrect. It's that it's bad form, right? It's like walking around in public in your underwear or something. It's maybe not that bad a form, but it's a matter of form, right? And so what we like to do in these cases is we like to do something called rationalizing the denominator. Okay, and so let's see an example of how this works. So what's the goal? So given something like 1 over the square root of 2, what we want to do is we want to rewrite the fraction so that the radical is not in the denominator. So given 1 over the square root of 2, we would like to re-express so that the radical, and that's just this thing, is not in the denominator. It's not in the bottom. We want to bring it up to the top. So there's a really simple way to do this, and this is a really simple thing to do. So if I start with 1 over the square root of 2, then I can multiply that by the square root of 2 over the square root of 2. Now, why can I do that? Well, if you recall, any number divided by itself is equal to 1. right? So when I do this, it's like I'm multiplying by 1. So it doesn't change anything, right? If another way to think about it is anything I do to the numerator, I also have to do to the denominator, and that's what this is doing. I'm multiplying both top and bottom by the square root of 2. Now when I do that, the top, in this case, becomes 1 times the square root of 2, so it's just the square root of 2. And what happens when I take the square root of 2 times the square root of 2? Well, I get the square root of 2 squared. And you might remember that when you square a square root, they kind of undo each other. Is one way to think about it. And this just becomes 2. Okay, so 1 divided by the square root of 2 is equal to the square root of 2 over 2. Okay. Now if I consider what I did up here with 5 over 2 square root of 5, let's take a look at that one. Okay. Now what I did there was I just multiplied the top and bottom by the square root of 5. So 5 over 2 square root of 5, and I multiply by the square root of 5 over the square root of 5, right? Again, just multiplying by effectively 1. Now in the top, I get 5 times the square root of 5. And in the bottom, I get 2. And then square root of 5 times square root of 5, again, that's square root of 5 squared. I'll write it out. Eventually, you won't have to write it out because you'll just know what it is. And what is it? Square root of 5 squared is just 5. Right, so I've got to multiply 2 times 5. So what I have here is 5 square root of 5 over 10. And of course, I can cancel 5 and 10, and I get square root of 5 over 2. Right, and that's what you'll see up here. Right, that's what we landed on up above here. Okay. And similarly here, all I did was multiply the top and bottom by square root of 5, and you'll see what happens is I have 5 divided by the square root of 5, and so that's 5 over square root of 5 times square root of 5 over square root of 5, like so. And up top I get 5 square root of 5. Down below I get square root of 5 squared, and so the square of the square root of 5 is just 5. The 5's cancel, and I have just 5, square root of 5. Right, which is what we have there. Okay. So that's rationalizing the denominator. In general, you're going to want to do that. I think if you are doing homeworks, the system may only accept answers where the denominator is rationalized. Okay. All right, very good. So now we've talked through the reciprocal identity, the quotient identities, and we've done an example and talked through rationalizing the denominator. Another identity that we will see is what's called the Pythagorean identity. Okay, and this one is obviously based on the Pythagorean theorem concept. Okay, so given a right triangle, here's the setup. Got a right triangle, angle theta, and the usual ABC, we'll say. Right, so given this kind of a setup, we know that a squared plus b squared equals c squared. That's the Pythagorean theorem. Now, in this expression, if I divide both sides by c squared, what happens? So divide both sides by c squared. So I get a squared over c squared plus b squared over c squared equals c squared over c squared, right? I just basically dividing everything by c squared. Okay, and again, we can do that. That's just algebra. Okay. So going forward with that, what does that lead us to? Well, just leaving these alone for a second, we'll come back to them. C squared over c squared is 1. Okay, so that's nice. Now, what about a squared over c squared? Well, another way to write that is a over c, and then square the whole ratio like that, square the fraction, plus b over c, square the whole thing. Okay. Now, what is A over C in terms of trigonometric functions? So in terms of trigonometric functions, what we're dealing with the adjacent side over the hypotenuse, that's the cosine. That's just the cosine, right? So this guy here is cosine of theta. And this guy over here, B over C, that's opposite over hypotenuse. That's the sine of theta. Okay, so this is the Pythagorean identity. So the Pythagorean identity says that cos squared theta plus sine squared theta equals 1. Okay. And the derivation is what we just did. Okay. Now, let's talk for a moment on notation. And when I say notation, I mean the mathematical symbols that we use. We'll frequently talk, not frequently, at least a couple of times we'll have to have an aside in the course to discuss mathematical notation, because there are some subtle things that are done in trigonometry notation-wise that we have to be careful of. And so one of the things that is done is the way that I've denoted the squaring here. So up above, I wrote cos theta squared. And so the idea here is whatever the cosine of theta is equal to, we're squaring it. Okay? So this is kind of the more like, if you have never seen the trig functions before, this is how you would expect to see the square of the cosine notated. But it turns out that in trigonometry there is a, and sometimes in other algebra, sometimes with function notation we see this as well, but certainly true in trig. This is oftentimes written just as cos squared theta, right? So the idea here is the same, right? So here, whatever the value of cos theta is, you're squaring it, right? And the same thing here. So if cosine of theta is 1/2, we're squaring it. Over here, it's going to be the same thing, right? So this is, sometimes we'll say cos squared theta. That means whatever cosine of theta is, square it, right? So it's just a little bit of a strange, a potentially confusing notational decision, right? But that's why I jump from here right to here. So cos theta squared is the same as cos squared theta. Sine theta, whole thing squared, is the same thing as sine squared theta. It's just the way we choose to notate it. It would get kind of confusing. The reason it's done like this is, right, because if you write cos theta squared, then there's a lot of ambiguity there. You're like, okay, wait a second, am I squaring cos theta, the value, or am I just squaring the angle theta? Right? The way to deal with that ambiguity is to put parentheses in here, but that gets kind of tedious after a while. If you have to write trig functions 1,000 times a day, that means you got to write 1,000 parentheses a day. And so instead of doing it this way, we have opted to write it like this, because it's both efficient time-wise, you don't have to write parentheses all the time, and it's also not ambiguous. Right? It's clear that we mean square of the value of the function here, not squaring the angle. Right? So that's why the notational decision exists. And but just take note that this is one of those things that you have to be a little bit aware of. Just be careful of. Don't let it confuse you. Okay. Let's do an example. Okay, so let's say we want to find the exact value of tangent of 20 degrees minus sine of 20 degrees over cosine of 20 degrees, right? So we want to find the exact value. And what is that, this expression, exact value, what does that mean? Well, you could always pull out a calculator and find an approximate value. If you plug in tangent of 20 degrees, you're going to get some decimal number, and it's an approximation of the tangent of 20 degrees. So when we say the exact value, what we want to know is basically what we're saying when we say exact value is don't use a calculator. Exact value means do not use a calculator. Okay. So exact value means do not use a calculator. More basically, that's what it means. Now, in some cases, you could use a calculator and get an exact value. It depends on the problem. But in general, the intention behind saying find the exact value is that we want you to use trigonometry, not just a computational aid to figure this out. Okay, and so this one is actually really easy, and it's by design. We'd want to start with an easy example of this kind of thing. So to find the exact value here, I just have to recognize something. Right, I have to recognize that I've got sine of 20 degrees divided by cosine of 20 degrees. Right, and I have to remember the quotient identity, that sine over cosine is really just tangent of the same angle. Right, so this expression is really tangent of 20 degrees minus this thing here, which is itself tangent of 20 degrees. Right, and so whatever tangent of 20 degrees happens to be, when I subtract that same value from it, I get 0. So the exact value of this expression is 0. Okay, so this is an early example of finding an exact value, and it's a simple one by design. Right, these can be as tricky as you like, but the idea, the goal with these kind of problems is to use the trigonometric knowledge you have gained to evaluate the expression in some kind of a clever way. Right? In this case, to recognize that sine over cosine is the same as tangent, and indeed you're just subtracting one value from itself. Right? And so you get 0. Let's see another example of this kind of thing. Find the exact value of sine squared pi over 12, that's a radian degree, a radian measure, plus 1 over secant squared pi over 12. Right, so it's an exact value, so we don't want to use a calculator. And this is going to be a similar kind of thing to the previous. So sine squared pi over 12 plus 1 over secant squared pi over 12. Well, here we just have to remember that secant and sine have this relationship. Oh, sorry, secant has a relationship not with sine, but with cosine. And so sine squared pi over 12 plus, instead of 1 over secant squared, we can use cosine squared. Right, and I'll try to note what we're doing here. So what we're using here is the fact that cosine is equal to 1 over secant. Right, and so cosine squared is equal to 1 over secant squared. Right, so that's what's happening here. Okay, and then what can we do? Well, I've got sine squared of some angle plus cosine squared of the same angle. That's the Pythagorean identity, and so we know that that's equal to 1. Pythagorean. Okay, so handwriting's a little messy there, but right. So this is kind of a two-parter, right? First, you find a useful way to re-express 1 over secant, and that useful way is cosine. And then you recognize that you've got sine squared plus cosine squared, which is equal to 1. Okay, and so the exact value here is 1. All right. Very good. Let's take a look at another example. And so this one, we're going to say if tangent of theta is equal to 1/2, what is the value of the other 5 trig functions? So this is a nice kind of problem here, right? So this is going to force us to really reason about this. So let's talk this out here. So tangent of theta, we know, is equal to the opposite over the adjacent. And we're told it's 1 over 2. Okay, so using this information, I can begin to construct a triangle. Right, I can construct a triangle here, not drawn to scale at all. The opposite side, so if this is theta, the opposite side is over here, and I'm told that the opposite side is 1. And the adjacent side is here, and I'm told that that is equal to 2. So I don't know c, though. Can I find c? Easily, right? A squared plus b squared equals c squared. And so c is equal to the square root of a squared plus b squared. And that means it's equal to, well, 1 squared plus 2 squared. So it's the square root of 5, right? Okay. And so given this is just a Pythagorean identity, so we'll say that this is a, well, it doesn't matter. So something like that. Okay, and so square root of 5 is what c must be equal to. So now I have the complete triangle. So given just the tangent, I can figure out what the complete triangle looks like. And once I know what the complete triangle looks like, I can derive all of the other 5 functions. So the sine of theta is the opposite over hypotenuse, and that's 1 over the square root of 5. 1 over square root of 5, and that can be rationalized as the square root of 5 over 5. The cosine of theta is the adjacent over hypotenuse, and that's 2 over the square root of 5. Okay, and that can be rationalized as 2 square root of 5 over 5. The cosecant, that's the inverse of the sine, so I'll just write as hypotenuse over opposite, and so it's square root of 5 over 1. So it's just square root of 5. The secant is the hypotenuse over adjacent, so that's the square root of 5 over 2. And what about cotangent? We forgot about that one. Well, cotangent is the inverse of a tangent. It's the reciprocal of 1/2, so it's just 2. Okay, so we got all of them. Okay, so that is a great little example of how to kind of get to all of these trig functions given just one of them. Right, so and this works for any of them. If you have any one of the 6 trig functions, you can quickly derive the other 5. Just using what I just did, that same kind of approach. Okay, all right, and so we've got one more thing to look at here. One more thing, one more topic. It's not too tricky of a topic, but it's actually a pretty interesting one. It's maybe a little trickier than the others, and that's what's called the complementary angle theorem. Right, and this kind of begins to hint at a lot of the amazing and subtle relationships that exist within triangles and the trig functions. So we have to start by defining what we mean by complementary angles. So 2 acute angles are complementary. That's the thing we're defining. Complementary if they sum to 90 degrees. Okay, so 2 acute angles that add up to 90 degrees are called complementary. Okay, so like 30 and 60, for example. 30 degrees and 60 degrees, when you add them together, you get 90 degrees. 45 and 45 would be a complementary pair. 80 and 10, 85 and 5, 75 and 15, okay, etc. Okay, and so here's where this is interesting. If we have a right triangle, right, so I got a right angle, and I've got another angle theta, and then let's say this third angle alpha. So given a right triangle, like this, given a right triangle, theta and alpha are always complementary. Okay. Maybe that's obvious, maybe that's not obvious. Let's think this through. Why is it the case? Well, I've got three angles here. I've got theta plus alpha plus my right angle, which I know is 90 degrees. Those three angles have to equal 180 degrees. Okay. I can do a little bit of algebra. I can subtract 90 degrees from both sides here. And what I see is that theta plus alpha is equal to 180 degrees minus 90 degrees. And further, theta plus alpha equals 90 degrees, right? So this is the definition of complementary angles. So theta and alpha always must equal 90 degrees simply because the other angle is 90 degrees and the three of them have to add up to 180. Okay. All right. Okay. And so now let's take this same kind of triangle here and let me put some, I'll move it down here a little bit. So I've got my theta, my 90 degrees, and my alpha. And let's say I have my A and my B and my C. Okay, so the sine of theta is equal to, we know that the sine of theta is equal to opposite over hypotenuse. Right, so if this is theta, then the opposite is B and the hypotenuse is C. Okay. What about the cosine of alpha? What about the cosine of alpha? So we have to be a little careful here with our reckoning, right? So now the angle of interest is alpha. Now we know that the cosine is the adjacent side divided by the hypotenuse. So in the case of alpha, which side is adjacent? This is the adjacent side, right? This is the side that's touching the angle alpha. Okay, so B over C. Adjacent over hypotenuse. B over C. So it's adjacent side to alpha. This is alpha. This is the side that's adjacent to it. So B over C. Okay, and you can see here that these are equal. All right, so the sine of theta equals the cosine of alpha. Okay. We could do something similar for cosecant and secant. Let's see. All right, so the cosecant of theta, we know that's hypotenuse over opposite. Right, it's the cosecant, the sine are the inverses, so it's the hypotenuse over opposite, so C over B. And the secant of alpha is equal to the hypotenuse over adjacent. Just reference your cheat sheet or your look back a few pages in the notes and you'll see that secant is hypotenuse over adjacent. And so here we're talking about the angle alpha. So here's the angle alpha, adjacent and hypotenuse. Hypotenuse over adjacent, so C over B again. And you can see they're equal. So the cosecant of theta is equal to the secant of alpha. Turns out that the same thing is true for tangent of theta being equal to the cotangent of of alpha. Okay, and so this is the complementary angle theorem. This is the reason the complementary angle theorem works. Let's actually state the theorem. Okay, so given a triangle like this, right triangle with theta and alpha, where theta and alpha are complementary angles. Okay, so given a triangle where theta and alpha are complementary angles, then sine of theta equals cosine of alpha. And I mean, you can reverse that and say cosine of theta equals sine of alpha. So the sine and cosine have this relationship to one another. The cosecant and the secant do as well. Cosecant of theta equals secant of alpha, and secant of theta equals cosecant of alpha. And the tangent and cotangent have the same thing as well. So tangent of theta equals cotangent alpha, and cotangent theta equals tangent alpha. Okay, so this is the complementary angles theorem. Okay. All right, and so these are the way this one is set up. It's set up along the lines of cofunctions. So sine, cosine, secant, cosecant, tangent, cotangent. So this one, that relationship is called the cofunction relationship. So sine's cofunction is cosine, cosine's cofunction is sine, and so on. And so this one is set up. This theorem operates along the lines of the cofunction relationship. Okay, so for an example, let's see an example here. So if sine of 30 degrees equals x, then cosine of 60 degrees, because 30 and 60 is 90, equals x as well. Okay. Similarly, if the tangent of 80 degrees, oops, I'll write that a little nicer. So if the tangent of 80 degrees equals y, then cotangent of 10 degrees equals y as well. Right, because 80 and 10 is 90. And another one would be if the secant of 45 degrees equals z, then the cosecant of what? 45 degrees equals z as well. Right, so the key is that these two angles here have to sum to 90. Right, and that the sine and the cosine, they have to be cofunctions. Tangent, cotangent, these are the cofunctions. Cofunctions, so I'll write it once, cofunctions. CO functions, right, just meaning secant, co-secant. Right, so the cofunctions. All right. Let's see one more example here, and then we'll call it. All right, one more kind of series of examples here. So let's say I have the sine of 62 degrees. Okay, then I know right away that that's equal to the cosine of 90 degrees minus 62 degrees, which is the cosine of 28 degrees. Well, how do I know that? Well, think about a triangle. Right, if this is, we'll say this one is 62 degrees. There's your right angle. 90 minus 62 is this guy. Okay, and so the cosine of this angle here and the sine of this angle here must be the same because they both sum up to 90 degrees and because they're cofunctions. All right, one more one more example, just to make sure that that's clear. Let's say I have a triangle. Let's say I have a triangle. I got a 90-degree corner here, and let's say I've got 75 degrees here. Well, I know automatically that this is 90 degrees minus 75 degrees, right? And we know that that's 15 degrees. Okay, and so the sine of 75 degrees must be equal to the cosine of 15 degrees. Right, you could do the same kind of thing with radians. You just got to be a little bit careful and make sure you're comfortable thinking in radians. Right, so if I have a triangle, 90 degrees here, and maybe this angle is pi over 12, then what is this other angle? Well, the other angle is 90 degrees, the radian equivalent of 90 degrees, which is actually pi over 2, if you recall. It's going to be that minus the pi over 12. Okay, and so it's actually 5 pi over 12. Right, and the way, and so what that means is that all of the cofunctions will be equal for this angle of like tangent. So we'll say like tangent of pi over 12 is equal to the cotangent cofunction of the other acute angle, which in this case is pi over 2 minus pi over 12, which I'll just do the math here for you. It would be like 6 pi over 12 minus pi over 12, and that's cotangent of 5 pi over 12. And so these two are equal, right? Pi over 12 and 5 pi over 12, that's definitely 6 pi over 12, also known as pi over 2, so 90 degrees, and they're cofunctions. Okay, so they have this cofunction relationship. All right, very good. So that's where we'll end this section, and I don't remember what's coming up next. I don't have it in front of me, so we'll see what comes up next when we get there. So we'll go ahead and end the lecture here, and we'll see you all next time. Take care.